Exploring the possibility of faster-than-light travel. The concept of faster-than-light, FTL, travel has captivated humanity for centuries. From the earliest myths of gods traveling in chariots across the sky to modern science fiction classics like Star Trek and Star Wars, the idea of zipping across the cosmos at speeds faster than light is something we all dream about. But is FTL travel actually possible? To answer this, we have to dig into the very fabric of space, time, and physics itself. Let's start with a simple fact. Nothing can travel faster than the speed of light, at least according to Einstein's theory of special relativity. Special relativity tells us that the speed of light, about 186,282 miles per second, is the ultimate speed limit in the universe. As an object approaches this speed, it requires more and more energy to accelerate, and at the speed of light, the energy required would become infinite. This suggests that FTL travel is not just impractical, it's fundamentally impossible within the framework of known physics. So if Einstein's theory is right, does that mean FTL travel is forever out of reach? Not necessarily. Let's explore some possibilities. First, let's consider wormholes, theoretical passages through spacetime that could, in theory, allow for faster-than-light travel. Wormholes are often depicted as shortcuts through the fabric of spacetime, creating a tunnel between distant points in the universe. If such wormholes exist, they could potentially allow for instantaneous travel between 2 points, even if those points are light years apart. But there's a major catch. We don't know if wormholes actually exist, and even if they did, keeping them stable enough for travel would be an entirely different challenge. Wormholes would require exotic matter with negative energy to stay open, and so far, this kind of matter hasn't been observed. The mathematics behind wormholes is sound, but their practicality is still a mystery. Then there's the idea of warp drives, a concept made famous by Star Trek. The Alcubierre drive proposed by Mexican physicist Miguel Alcubierre in 1994 is one such theoretical example. The Alcubierre drive involves contracting space in front of a spacecraft and expanding it behind, creating a warp bubble that moves faster than light. Inside this bubble, the spacecraft itself wouldn't be moving faster than light. Instead, space itself would be moving around the spacecraft. This allows it to effectively cheat the speed limit set by relativity. While intriguing, the Alcubierre drive comes with its own set of problems. First, it would require an enormous amount of negative energy, the same kind of exotic matter needed for wormholes. Even if negative energy were somehow achievable, we would need a massive amount of it to warp space on a meaningful scale. Then there's the problem of safety. Traveling at faster than light speeds could cause violent shocks to anything in the spacecraft's path. Even a tiny particle of dust traveling at FTL speeds could cause catastrophic damage to the spacecraft. Even if we could theoretically build an Alcubierre drive, we'd still have to figure out how to control the warp bubble, protect our ships, and handle the enormous energy requirements. Another potential avenue for FTL travel is tachyons, hypothetical particles that always travel faster than light. If tachyons exist, they could potentially be harnessed to send information or even objects at FTL speeds. However, tachyons are purely speculative, and there's currently no evidence that they exist. Moreover, their very nature presents strange paradoxes, such as the possibility of time travel, which further complicates the idea of using them for practical travel. Even more mind-boggling is the idea of quantum entanglement, which Einstein famously called spooky action at a distance. In quantum physics, entangled particles can be linked in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. Some have wondered whether this phenomenon could be used for FTL communication, or even travel. While quantum entanglement is real, it doesn't violate the speed of light limit in a way that allows for FTL travel. The key issue is that while entanglement can link particles across vast distances, it can't actually transmit usable information faster than light. It's more of a curious phenomenon than a practical method for space travel. But what if we take a step back and think about space-time itself? What if we could manipulate the very structure of the universe? In recent years, scientists have proposed the idea of space-time foam, which suggests that space-time might not be smooth, but instead foamy at the quantum level. If this is true, it could open the door to new forms of travel that we can't even begin to comprehend yet. Perhaps in the future, we could develop the ability to reshape space-time on a quantum scale, allowing for faster-than-light travel in ways that we can't predict right now. But for now, this is purely speculative. The question remains, are we stuck with the speed of light as our upper limit, or is there a hidden loophole in the laws of physics that we just haven't discovered yet? As it stands, the answer leans heavily toward the speed of light being the limit. But space is vast, and our understanding of the universe is still in its infancy. It's possible that in the future, we may uncover new principles of physics that challenge what we currently know. Perhaps the speed of light is not a universal constant, but rather a limit of our current understanding. Or perhaps, with the right breakthroughs, we'll learn to travel beyond the stars in ways that we can only imagine today. In the end, faster-than-light travel is one of the great mysteries of the universe, and while it's unlikely that we'll crack the code in the near future, the journey of discovery is just as important as the destination. For now, we're limited by the speed of light. But with each new breakthrough in science, the dream of traveling to distant stars remains alive. And maybe, just maybe, one day, we'll find a way to break the barriers of time and space and truly explore the cosmos.